Welcome back to the HVAC-Engineering-Techie channel. This is the channel that talks all things HVAC. Engineering design, construction, equipment, systems, test and balance extensively, controls, efficiency, and system performance. These videos are intended to be educational in nature to help you with your career and to help you on the job. Today's lesson is on hydraulic balancing of hot water systems. This is another one in the series of how to actually balance systems. So this should be helpful to you. Before we get started, if you're not already a subscribing member, would you mind doing that for me? I'd really appreciate it. All you have to do is click that subscribe button down below and give me a thumbs up if you like the video. It's free. It doesn't cost you anything. It's absolutely painless for you, but it's very, very helpful to me, and I would really appreciate it. And the reason is Google uses that data to evaluate this video, and that would be extremely helpful to help me stay on the air. So thank you in advance for doing that. So let's get started with hot water systems today. Let's review hydronic system basics to kind of get an idea of what these systems are. So basically, in our HVAC, we use hot water. We do use steam once in a while, but mainly we use hot water. So hot water is basically a system that has a boiler that generates the heat for the water and raises it up in temperature. And it goes to the coil, it heats the air in the coil, or it's a heat exchanger. Then we have a control valve. It goes down to the suction of a pump, and this pump puts water back to the boiler. Now, sometimes you'll see a pump like this in a different configuration where the hot water goes to the suction of the pump. That's not actually good engineering practice, because hot water increases the requirement of net suction head. And so if you have really hot water right into the inlet of the pump, it can help it cavitate. So we don't, normally this is the condition we like, with the coldest water in the system coming to the pump pumping to the boiler. Another thing is, remember, the control valve is always on the return side of the coil. That's to prevent air lock. If you put the valve up here, it can encourage air bubbles to exit the water and perform air pockets in the coil. And if it does that, you'll end up with plug flow in the system. It doesn't hurt the boiler, of course, but it's really hard to transfer heat without any water in it. Remember that heat always flows from warm to cold. So if you have cold air in a hot coil, the air is going to get warm. The total BTU exchange is dependent upon the temperature difference, the delta T, the flow of the GPM, how many GPM you got going, the sensible heat of the fluid, and the heat transfer conditions of the heat exchanger. So the heat exchanger, so depends on how many fans it has, how many rows it has, and what is the total surface area it has to exchange heat. It also matters what the temperature difference is between here, and it also matters how many GPM you're putting through it, and of course the specific heat of the fluid. If you put glycol in here, its heat efficiency is going to go down. Glycol saves it from freezing, but it doesn't help transfer heat. Building hot water systems normally have a temperature set point from 90 to 180 degrees. The set point of 180 degrees, of course, is designed to keep it below that 212 temperature that it turns to steam. We don't want steam in a hot water system, so that's why we maintain it to no higher than 180 degrees. Unless it has high pressure. A high pressure system, you can get to 220 degrees without it turning to steam, but we don't see many of those anymore. All water systems must be totally full of water and have no air pockets at the high points of the system. So it's important that we have 100% water in the system. We can't have any air in the system. And the chemical treatment systems are required to limit corrosion and scaling. So this is a closed loop system. So normally we put a pot feeder on here and we'll feed chemicals to, once this system is flushed and cleaned and its detergent is cleaned and then flushed again, they'll use a chemical to passivate the pipe. Keeps it from corroding, and that's the kind of chemical treatment we put in there. And it should be in there before you start test and balancing and running water around the system. It should be passivated. Running raw water around a system will cause it to start to corrode, and that'll just make it corrode that much faster. So they should never run a system without it being pacified. Okay, let's look at the pipe systems. This is a normal hot water system with a boiler and a couple of pumps. And it runs it around, and these are three-way valves because this is a constant flow system. We have a pump system, and the pump assembly has a flex connectors to keep the vibration of the pump entering the system. Has a check valve to make sure when this pump shuts off, this water doesn't come, it stops the water from flowing backwards. We have a couple of shut-off valves in case we need to work on the pump. And we have a strainer. Right here is a suction strainer. And then we have a pressure gauge header here. And remember that the pressure gauge header should be connected directly to the inlet of the pump and directly to the outlet of the pump. That's what we need to be able to read the pump curve. If for any reason they take this and put it up here, or take this one and move it up here, then we cannot use it. So it means we can't balance the pump. So these always have to be done correctly. It is correct here in that using one gauge. We use one gauge to eliminate the inaccuracy of a gauge. If you have two gauges, one could be inaccurate, and you'd be reading that as a differential pressure. We want to be able to read the same gauge that gets rid of the inaccuracy gauge, and we can read differential pressure. We have a coil systems, and they have a control valve, shut-off valve. We have shut-off valves. We have a balance valve. We have a strainer, bleed and drain valves, and hose flex connections normally. It depends. If hose flex connection shouldn't be used on anything above 1 1/4 inch. At that point, it needs to become pipe, fixed pipe. If you have a 2-inch coil, it certainly needs to be pipe and no flex connections in there, or no flexible tubing in there. So the shut-off valves, we have the shut-off valves over here. We have a balance valve and we have a control valve, and this is a 3-way bypass valve. So we know that the water normally flows in and goes through the coil when it needs heat. When it doesn't, it'll start bypassing. It'll modulate between these two. It'll modulate between the coil and that. So when we balance these coils, we have to balance this valve here to balance the flow to the coil. And then we have to change it from the flow to go to bypass, and then we balance this valve to equal the pressure loss of the coil, so that this system never sees a pressure change between flowing to the coil and bypassing the coil. This system thinks it's the same thing. It doesn't know. Strainers should be there to protect the coil. So if you have a reheat coil that has 1/4 inch tubes or 3/8 tubes, you need to have a strainer in front of them. If you have a coil that has 1-inch tubes, you don't need a strainer in front of it. And the reason is because the main system strainer probably has 3/8 inch sieve in it. So it'll catch anything that could possibly clog this coil. So you don't need strainers at every single coil. We only need them to protect the coil when it's capable of being able to be clogged by debris in the system. We have an expansion tank here, and the expansion tank is designed to have a cushion of air in it, so that when the temperature changes of the water as it expands and contracts because of temperature change, this allows it to not change pressure in the system. It will just, that water level will go up. When the pressure increases, it'll go down when it decreases. That's what expansion tanks are. Most modern expansion tanks have air bladders in them, so the water and air are separated. The traditional tank was an open tank. It was a closed tank, but it had a water. We put an air charge on top of the tank, and the problem was over time, the air will absorb into the water. And so ever so often you had to go in and drain a tank and put an air charge back in it, or else it wasn't effective. Another thing about this particular system is we have a dirt removal device. This is a centrifugal debris removing device. So as the water is pushed from the system, comes back and it twirls and it removes any debris, and then it goes to the systems. Here we were using this one. It has an air vent on top, and we were using this to get the air to the expansion tank. And then we have a relief fitting up here that will allow us to change the height of the tank. It also has an inlet water here, which has a backflow preventer and a pressure reducers, and it sets the system pressure here at the inlet of the pumps. It doesn't have to be in this this removal device. You could pipe the expansion tank directly to the inlet pipe, but it is very important that the pressure gets set at the suction of the pumps, like every other system, whether it's chill water or hot water. And that's how we do that. And remember that the pressure setting you use there, that's something you have to do. You should measure from this distance clear to the very top pipe of the system. Divide that and add a couple of feet, divide by 2.31, and that'll equal the PSI that must be. If you set it anything less than that, you will cause air pockets in the very top of the pipe. When the system's off, the water will drain down to its natural level and create a vacuum up here, and these pipes will actually have a slug of air. So when they turn them on, that slug of air goes through the system. So we don't want that. We want it to be totally full of water. All right, this is a reverse return pipe. It's the same as the other one, except what we're trying to do with a reverse return is we're trying to equalize the path of the pipe. So we have equal pressure drop for all coils, because this pipe, you notice this pipe is a supply pipe, and it goes up and it feeds this coil first, this coil second, this coil third. And if you have just a regular pipe, then it also has the longest path in return. So this one can have more pressure, this a little less pressure, and this the least pressure. If you do a reverse return, now this coil and this coil have exactly the same pipe distance, because we've doubled this up on the return. And that's what a reverse return is. It's more efficient, they're easier to balance, and they make the process, and they can be a loop pipe. Okay, so instead of this pipe running right along the side, it can be a loop pipe that goes around a building like this, and that's also a reverse return. So anyway, reverse returns, very popular. It works well. Sometimes we don't use it because of money, but it sure makes the system better. Then we have what's called a changeover system. Changeover systems used to be really popular, not so much anymore. And the reason they were used, of course, is because of cost. When you have a two-pipe system with heating and cooling, they switch between cooling cold water and heating hot water. And obviously the problem is that everyone is either in heating or in cooling. You can't be this one in heating, this one in cooling. So these systems are discouraged, and four-pipe allow you to heat and cool anywhere you want, but not with these systems. So this system is the same as the other system we just looked at, as a primary pump, as a lead pump and a lag pump, as a debris moving device. And the water circulates from the load back down to the chiller, and then through the boiler, and then through the suction of the pumps, and out pressurized to the coils. Now, this is a regular system, so when it's in boiler, we don't want the chiller tubes open, so we bypass the chiller. And when we're in chiller, we don't want the cold water going through the boiler, so we bypass the boiler. So the reason we don't want it going through these is this one, especially if you run cold water through it, it'll condense on the tube. If it's a water tube boiler, it'll condense on the tubes and ruin the boiler. So you can't do that. You have to take the boiler offline and not run the cold water through it. Same with the chiller. Don't run hot water through the chiller. You can, but you get migration issues on refrigerant and things like that. So you need to get them out of the circuit. Another thing about all the systems you looked at so far are constant volume systems. And a thing about, on chill water systems, we worry about diversity. We want to make sure that the water to all these coils matches these pumps, the boiler flow and the chiller flow. However, there should never be diversity in a hot water system, period. Now, you may see diversity every once in a while. If it is, it's an error. And the reason is because diversity is due to the sun not shining in all aspects of the building at the same time. So as the sun moves around the building, the load moves around the building. So you don't need to have that 100% load all the time for chiller. But a boiler is heating, and when it's cold and cloudy and rainy, it's cold everywhere. No sun shining on it, so there can't be diversity. Now, there may be some diversity if they have something strange going on, like they have large coils in the air handler for morning warm-up, and then when that's done, they switch to reheat coils. And that's not really diversity, but we do move the water around. You just have to be smart enough to understand that they don't work at the same time, so you don't have to calculate them. But really, there should be no diversity in hot water systems. Changeover systems, the central plant delivers cold water for cooling during the summer and hot water during the winter. The big problem is determining when it's summer and when it's winter, right? Because, if you use outside air, that may not work because that's an open loop. It's not a direct loop. You could use, you can't really use valve position, and we're going to talk about that right now. Here's the coil, but the problem is these valves have to change their polarity based upon whether they're heating or cooling, because In cooling, you want to open this valve when you need more cooling, and in heating, you need more heating when you open the valve. Well, those are opposites. So it needs to, in cooling, it needs to know that it's in cooling so it can reverse the action of the valve. So here's, if you didn't add it, if you're in heating and it had cold water in it, the heating would say, if I'm too cold, I want to increase more water. And it's cold water, so you'd be making it worse. You'd be cooling the room instead of heating it. So what we normally do is we have a system up here on these valves, and we either put a local temperature sensor, so when we have cold water, we can switch its action, or we can just get a signal from the central plant controller telling us that these are now reverse acting. So either way works. In the old days, of course, we used a local temperature because we didn't have really good communication, but that's not true anymore. Coils are sized for cooling load, normally too large for heating load, unless the outside air load. So when you're designing one of these, you'll use your biggest load, and normally it's cooling, unless it's in some really cold place where it's all heating, then that would change, but you need to size it for the worst load conditions, which just means it's too big a coil for the other load. So if it's too big a coil for the load, it doesn't really hurt anything. It just gets the temperature quicker. So that does work. Here's another weird one. This is one you will almost never see, but you will see it once in a while, where we have one coil on a 4-pipe system. So we have a system that has hot water pipes and cold water pipes. Hot water for winter, cold water for summer, but we just have one coil. We have to requires a system switchover valve. So we have the same problem, is that we have to switch the action of this valve depending on whether we're cooling and heating. But we have a second problem, in that we need to separate the coil control valve. So what we do is we have these deflecting valves that actually change it to attach it to the cold water system or attach it to the hot water system, depending on what season we're in. So requires control action, switch over from system, switch over valve. So this is a little more complex, the system. They ask, why would we ever use these coils? Well, where I've seen them lately is in large outside air systems that aren't going to be required to do much dehumidification. You can do some. You can still do dehumidification by running the coil cold and having reheat downstream in the rooms. So that does work, but normally we just have one coil because an outside air system never has to heat and cool both. It can either be heating in the wintertime or cooling in the summertime, because it's never really doing a lot of load. It's just trimming off the outside air. So they do this to save cost. I'm not sure how much cost it actually saves. It seems all this trouble you have to go through is negating the cost issue, but they have to do it. Alrighty. So let's talk about pre-balance. We've done this on the other sessions if you looked at them. Before you do anything on a job, you need to get the drawings, go through the drawings so you learn the job. You need to know what's going on out there before you get there. The first thing you want to watch out for is, do flows and components match? You're doing a design reviews. And this is a heating system, so we should not have diversity. Now, I've seen heating systems where the coil flows don't match the pump flows, the pumps don't match the boiler flows, and the boiler BTU capacity don't match the coil capacity. That's a mess. They need to actually match. And it means in the schedules, they may not put, in a schedule you have two choices as a designer. You can put in the piece of equipment maximum values, or you can put in the actual value you need for the job. It's your choice. So as a tab guy, you should understand that what's on the schedule may not actually be what's on the coils. Now, if that's true, the one in the schedule needs to be larger. They either need to be the same, or the one in the schedule needs to be larger. Boiler flow needs to match the primary pumps. Boiler makeup water systems, higher pressure than the boiler systems. So when you're putting makeup water into a boiler, it has to be, your makeup water pump has to be big enough to put pressure in the system. A total flow of all connected coils to primary and secondary pump flow. Hot water systems should never have system diversity. If you have diversity, you need to find out why. Is there something special, or was this an error? And the only way I know is to talk to the designer. Review design of system effect issues, increasing water velocity down the piping system. Normally the velocity gets lower the further you go with the pumps. And remember that system effect is basically something that adds significant pressure at downstream away from the pump. So if you remember, the pump will add velocity and pressure to the pipe to get the water right flowing from the pump. And as the water flows down the pipe, the wall resistance slows down the water and changes the pressure from velocity pressure to static pressure in the pipe. And that happens for free. It doesn't cost anything. It will automatically go from velocity pressure to static pressure because you're flowing it down the pipe. But now if you go down the pipe and all of a sudden you were traveling at 5 feet per second, now you want to take it to 10 feet per second, that's not free. That takes horsepower. And that's what we're trying to not have. We're trying to make sure that we have enough pressure at the pump to do everything downstream of it and not have this problem. So the designer should not have higher velocity pipe downstream than he has at the pump. The velocity should be that way. It doesn't matter really. I mean, they'll take that into account, but abrupt changes will basically require more horsepower. And it's not that he didn't calculate, he should have calculated that in, but we shouldn't have it. The things that really drive this crazy is bullhead tees. Should never have a bullhead tee. A bullhead tee can always be done differently with a T and an elbow. Completely removes the requirement of bullhead tee. And a bullhead tee, of course, is where water enters a side inlet of a T and is expected to go out to the right branch and the left branch. So it breaks and goes both ways. Tees are designed in water to let water in, but the water is going one direction. So it comes in and goes out, or letting it go out. It's traveling along the path and then it goes out the side outlet. That's fine. But a bullhead tee is where the water goes in and has to go both ways, or even worse, where the water is coming in from both ways and is expected to go out the side outlet. Those are terrible. And the reason they're bad, they're very high loss pressure. But the problem is if you change flow just a little bit, you can have a drastic change in the static pressure and what's flowing on both those side outlets. It's capable of being a 200% difference. So never use bullhead tees. There's no reason for it. It's just done by people who don't know any better and have little experience. So try to always not allow a bullhead tee. Bullhead tees are a big problem, especially if the velocities are high. If the velocities are very, very low, it doesn't make much difference. Because if the water is not as much pressure drop going through that tee, it won't matter a lot. So, if you have velocity down at 0.5 feet per second or something, it's probably not going to make much difference. But if you're up around a normal design flow of 4, 5 to 7, it will make a significant difference. Okay, and then once you've done that, you need to go to the field and do a site review to see where you were at. Because you can never trust a contractor to actually schedule you correctly. They have a need, they have a schedule, and they need you out there. But if they're not ready, it won't help. It certainly won't help you. So do flows and pressures of pumps and equipment match the design? So did they install things that actually match the design? Do pumps have the right flow as per the design, the right head? Is the boiler the right size, the right capacity, have the right water flow? That you need to check. If you don't check it, who will? Hopefully the mechanical contractor, but you can't rely on that. You got to make sure. Has the piping system been cleaned, flushed, and all water treatment chemicals applied? Have all pipe strainers been blown down and are verified clean? And remember, the big strainers should have been installed with startup screens. So on those strainers, the main sieve in there, the holes in the sieves should be slightly smaller than the holes in the volute pump, the pump wheel. So if the pump wheel has 3/8-inch holes, you need to have a sieve that has 1/4-inch holes. It needs to be smaller because it needs to protect the pumps. And we say, what is it protecting from? Any debris in the pipe. You get a joker on the site that pours plastic peanuts in a pipe, you can't imagine what that does to a pump. So you need to make sure those sieves are there. Now, they put a fine sieve inside, and it's designed to catch the scale in the pipe. So it's really fine. But those are intended to be removed after startup. And if they're not, boy, your balance is going to really be screwed up. So you really need to make sure those are removed. You don't want to do it because that's part of the mechanical contractor's job. You just want to verify they've been cleaned. Is the system totally full of water and makeup water set at the correct pressure? Always check that pressure. Now, how do you know if it's got air? Well, the way to tell if it's got air is one, by sound. If you have a lot of air in the pipe, you will hear it when it goes through pumps, when it goes through the coils. You'll hear that air. Or go to the high point of the system and manually open the bleed valve. If water pours out, it probably doesn't have any air. If it blows air, you know you got air, and that's what they're for, is to remove the air. But if you got enough, if you have an air blockage up there, or if you have an air bubble, it will blow air for some time. Sometimes it'll blow for 3 or 4 minutes. Normally put a hose on it into a bucket so we don't make a mess, but you have to make sure there's no air in the water. Is the makeup water system installed at the correct location? Is it set to set the pressure at the suction of the pumps? Are pump pressure measurement gauges or ports installed correctly? You have to check this on every job. We find this wrong many, many times. Review piping installation for bullhead tees. We shouldn't have any. Review installation for system effect issues, increased water velocity. We don't want any of that. No bullhead tees. All right, so let's look at a constant volume water system. Now, this is a typical hot water constant volume system. You can tell it's constant volume because it's got 3-way valves on the coils. So the water flowing through the coil, and when it's not needed, then it's bypassed or it's modulated. So the some would be maybe going through the bypass and some to the coil, but it means the water here should always be the same whether the coil is using the water or not. So that means the flow in the system is totally constant volume. System, of course, has a lead pump and a lag pump, primary pumps, and it has a boiler. It may have more than one. So basically, this is sometimes the boiler will have its own primary pump, and these would be secondary pumps. But in this simple design, this is a primary pump, and that's the boiler. So the design, of course, is the pump pumps through the boiler. It goes to the load, through the coils, and back to the sediment removing device and into the suction of the pumps. And again, this expansion tank is setting the pressure right at this debris removing device. But it could be over here to the pipe. This pipe here doesn't matter. Of course, it has an inlet water here with a backflow preventer and a pressure reducing valve. And of course, that's where you need to set the pressure to make sure that your pressure is greater than this total height divided by 2.31. So this PSI should be great enough to push the water up here when the system is off. So what happens is this sets the pressure, say it's 20 pounds or whatever it is here. Now on a single story building, it might be 10 or 12 pounds. And then the pump adds pressure to it, and that pressure the pump is adding to it is enough to get past all the friction losses of the system. If you put the makeup water here and it sets it to 10 pounds, then this is going to go to a vacuum probably. So basically, you just can't do that. It has to be on the suction side of the pumps. Now, one of the problems with a boiler like this, normally these smaller systems or water tube boilers, could be, if it's a bigger system, it could be a fire tube boiler, but on a water tube boiler, we have a problem if we allow water to condense onto the tubes. It will rust the boiler away in a very short period of time. I've seen it totally destroy boilers within 3 months of operation. So what they do is they want this water to be hot, and the manufacturer will tell you the minimum leaving temperature. And normally it's around 130 degrees, it might be 138 degrees, it might be 125 degrees. But that means the temperature in the system can't be less than that temperature. That's why this is a design that maybe if you have a fire tube boiler, you don't have to worry about it because fire tube boilers are already coated in water. It doesn't matter. But if it's a water tube boiler, it matters a lot. All right, that's constant hot water temperature system. Let's look how we control these things. So typical control sequence, the system shall be enabled based upon an occupancy schedule. Start the lead pump. After confirmation of flow, enable the boiler. The boiler has its own controls and it will maintain its temperature. If after 5 minutes any pump fails, start the lag pump and send an alarm. Hot water supply temperature set point should be 140 degrees. Hot water temperature shall be reset based upon the heating and valve position. Reset range should be from 130 to 180 degrees. So we can still reset it. We just can't reset it very low. It has to be from 130 to 180 degrees or whatever this minimum temperature is. Monitor all temperature sensors. If hot water temperature drops more than 3 degrees below set point for more than 15 minutes, send a trouble alarm. Monitor the hot water supply return temperature and the outside air temperature and humidity. So that's a typical central plant system for hot water, constant volume system. So how do we balance this system? All right, so test the pumps and boiler to make sure they work. They provide flow and correct temperature. Verify all coil balance control valves are 100% open. Now remember, we have a control valve, we have a balance valve, and before you start, you need to command all those control valves to 100% open, and you need to manually make sure that all these balance valves have been left open. Now, normally that's not hard because normally balance valves come open, but you got to check to make sure someone hasn't closed them for some reason. Okay, balance system pumps to design flow with the coils all open and the valves all open. Balance the flow to 5 to 10%. Measure shut-off head and total flow head. Record all pump voltage, amps, pressure, inlet pressure, outlet pressure, and total flow. So the reason we're setting it up just a little bit high is because when we come down here and do our balancing, we're going to cause some back pressure, which will run these pumps up on our curve, and we may have to come back and trim them off again to a little bit more flow. Okay, then we're going to pre-read all the balance valves without balancing anything. We're just going to go out and read all the flows. And then we're going to, if we're going to use it, there's two types of systems to do these valves. You're going to use a series system, or you can use a proportional system. And to see how to do that, you can see our session T7. It's on how to do both these series. It tells you how to do a series balance and a proportional balance. Yeah, so the series system, if you use a series balance method, start at the coil with the highest flow and adjust balance valve for correct coil flow. Move on to the next highest valve flow and continue to all coils are balanced. If using the proportional balance method, start at the lowest coil and balance each valve. Once you go out here and you read all these balance valves, and then you relist them in a list. And if you're using a series, you put the highest percentage flow at the top, lowest percentage flow at the bottom. If you're using the proportional method, do exactly the opposite. You'll list the lowest percentage valve first, the highest percentage last. And so the process is you push water to that target valve. So you have one valve in the system that you don't ever touch. You don't balance it at all. You leave the valve 100% open. That's what you're trying to do, is the lowest possible practical operating pressure. To do that, one valve has to be open. Okay, verify flow and pressure drop across the boiler, record flow and inlet and outlet temperature. So once you've set up the pumps and you've got these coils all balanced, record pump and pressure, operating pressure, record backup water pressure, and don't forget to release these valves to automatic operation, right? Because you had them 100% open. By the way, I forgot to mention that when you do this balance out here, this process, you're going to balance these balance valves. Once you have this, you open the valve 100% to the coil, and then you balance the balance valve. And once you're in balance, then you take this coil, the valve, and you command it to bypass. And then you go to this balance valve, and you make sure this balance valve equals the loss of the coil. Whatever the pressure drop of the coil was, you set this balance valve to equal that pressure so that when this system is running to the coil or running to bypass, the system sees no pressure difference. The flow stays the same, so you have to balance the bypass. Now let's review a variable hot water system. So you can see this system has two-way valves on the coil, so as it changes temperature, it reduces the water flow or increases the water flow to the coil. This makes it a VAV system. So we have a secondary pumps, we have a lead pump and a lag pump, and we have primary pumps on the boilers. So they're dedicated to a boiler. So we have a primary pump system, we have a secondary pump system, and one boiler's lead, one boiler's lag. So the way this works, of course, is the pumps pump the water into the boiler systems, into the suction of the primary pumps. The pumps then pump the hot water to the field. The hot water is using the coils and is returned to the sediment removing device and into the suction of the secondary pumps. Again, we have an expansion tank, which has a pressure reducing valve, which we set the pressure. I show it going into the sediment removing device, but it could go into the pipe. Remember, that's set to keep this full of water up here. Divide the height by 2.31, and you have to have at least a little bit higher pressure than that to make it work, so we don't have any air bubbles. These pumps here are constant volume. We have a decoupler. So if this system starts lowering the flow, then some of this flow starts bypassing back to the boiler. So this is doing that. And then this one's taking all the water it gives because it's got less flow. If for some reason this has more flow than this side, then it goes in the opposite direction. So this is the boiler going this way, and this system would go that way. So at this point, it would be mixing the return water with the supply water until it gets too cold, and then it'll go back the other way. So basically, this is the operation of a variable volume hot water system. So how do we control a system like this? Systems shall be enabled based upon an occupancy schedule. Start the lead pump. After confirmation of flow, start the lead primary pump and enable the boiler. Internal boiler control shall start the primary pump and stage the boiler burner to maintain leading boiler temperature. Most of the times these are started with the boiler, but you could have a system, this might be a larger pump somewhere that might be started by the control system. After 5 minutes, the lead pump fails, then start the lag pump and alarm. If the system hot water supply temperature drops more than 3 degrees below set point and the lead boiler is at full fire capacity, then start the lag primary pump and boiler. When both boilers are below 40% capacity, stop the lag primary pump and go back to just the lead boiler. The boiler hot water supply temperature set point should be 140 degrees. Hot water supply temperature should be reset based upon the heating coil valve position. Reset range should be from 130 to 180 degrees. And remember that 130 degrees is set by the minimum temperature coming out of the boiler. We're not able to reset temperature down below that because we will harm the boilers. System pump speed should be modulated to maintain differential pressure set point as set by tab. Plus minus 15 might be plus minus 20. We'll talk about that later. Monitor all temperature sensors. If hot water supply temperature drops more than 5 degrees below set point for more than 15 minutes, send an alarm. Monitor the hot water supply and hot water return temperature and outside air temperature and humidity. Control is pretty simple of these systems. Now let's talk about balancing them. So test the pumps and boiler for operability. Verify the units provide flow and temperature. Verify all coil balance and control valves 100% open. So again, command these valves to 100% full open and lock them that way. Don't allow the system to modulate them. And then make sure the balance valves are 100% open. Balance the boiler primary pumps so that the boiler has the right water flow to maintain 130 degrees. And that you can actually calculate if you know the BTU of the burner. So you can calculate that flow to set the flow. A balanced system pump, or else you can have the system running and you can just tell, by measuring the temperature. Balance the system pumps to design flow plus 5 to 10%. Measure shutoff head and total flow head. Record all pump voltage, amp, speed, inlet pressure, outlet pressure, and total flow. So now that we got the pump set up, what we do, we got the field blocked open at design flow, and we've got the pump set up for design flow. So we set these pumps first, then we set these pumps, and then we make sure we have this block of water matches this block of water, and our job now is to go balance that flow with these pumps locked in position. So what you want to do is you want to lock these pumps. These pumps have VFDs. You don't want to leave them in automatic. You want to take the VFD, turn it to manual mode, and put a speed in that gives you the flow from the pump curve. So you've read the pump curve and know this is if I need 150 GPM or 200 GPM. I have this flow going to the field, and now we can balance that flow. If the system has diversity, close enough balance valves so the coil flow equals 100% of primary flow. There should never be diversity in a hot water system, because when it's cold outside, you need all these coils could be at design flow at the same time. So there really shouldn't be any diversity, but if there is, you still got to deal with it. You got to balance it. If you find it during the design review, you need to talk to the designer and ask him, not sure why there's diversity, and let him explain that to you. Pre-read all balance valve flows, balance with all the balance valves 100% open. Don't balance anything, just read them all. And if using the series balance method, started the coil with the highest flow, so you're going to take what you read up here and you're going to resort it into a schedule so you can follow it. And if you're going to use a series flow, then the highest to lowest. If you're going to use proportional method, you do it exactly opposite. You go from lowest to high, and then you start at the top and work your way down the list. There is a session called T7, like I said before, that'll tell you how to do proportional and series balance flows. The key is that one of these valves is going to be 100% open and we're never going to touch it. That's your target valve. That's your lowest valve. And you're going to push water to that valve to make sure it has it. And that's how you're going to balance. Both the series and the proportional balance methods work. Proportional is a little more work, I think, and takes a little bit more feel for it, where proportional balance is simple, and you don't need to have a bunch of feel for that. That's just plain simple. Anyway, you need to get used to doing those one way or the other. Open the coils that were closed to provide diversity flow, and close the other coils to meet the diversity flow, and balance those. So you can see T20 for diversity flow, how to do that. But again, hot water system shouldn't have any, so you shouldn't have to do that here. With the coils locked 100% open, this is kind of key here. With the coils locked 100% open, with a control valve locked 100% open, and the balance valves balanced. Okay, so we got flowed all the coils and they're all balanced. And the system pumps are still locked in flow. We go back and look to make sure they still have the right flow. And if not, we speed them up just a little bit so they have the right flow. Now we know our coils have the right flow. And at that point, you're going to read the differential pressure on the control system. What does it tell you the supply pipe system differential pressure is? Whatever that is the set point you need to run the system. So record that set point and then program that into the control system that this will be the system set point. Now, a lot of guys will go out there and set the set point up and then try to balance it with it in automatic. And the reason that doesn't work is because as you're balancing, you're changing the back pressure, and your control system will be trying to get rid of that back pressure by modulation. You don't want that. You really want it set up so you can tell what the set point will be. What people that do that are always playing with the set point, trying to get it where they get enough water. That's a total waste of time. It's better to set the system up correctly, and it'll tell you exactly what pressure point it needs to be, and not close. It'll tell you exactly. Release all controls to automatic operation. Don't forget to do that. Balance boiler primary pumps to provide the required leaving temperature, normally 130 degrees. Verify flow and pressure drop across each boiler. Flow and in and out temperatures. Record pump flows, operating pressures. Record makeup water pressure set point. It's always important to do that because sometimes operators don't actually know what it should be. And if you've got it in your report, they'll have a document telling them how to do that. So now we're going to talk about variable temperature hot water systems. So we've talked about constant flow systems. We've talked about variable flow systems, and now we're going to talk about variable temperature systems. Now, it is possible. I didn't show one because it gets complicated. It is possible to have both variable temperature and variable flow. It is possible to do that. Now, this one I've shown as a constant flow system, just variable temperature. So the way this works is we have three-way valves, which makes it constant volume. We have secondary pumps. We have a lead and a lag secondary pump. We have one boiler with a primary pump. So the way this works is that the boiler gets its water. This pump pumps the water from the system through the boiler, and this is balanced to give that 130, 140 degrees, whatever we need to not ruin the boiler. And that water flows to the system, to the coils, and back to the debris removing device and back to the suction pumps, and it starts over. The way it varies temperature, it's got a temperature probe here, and what it does is it watches the temperature, and if the temperature gets too high, it starts taking some of this water and mixes it with the hot water. When that happens, this now uses this decoupler and starts flowing some water this way. So whatever water you put this way now goes this direction. So, and if the water gets too cold, then it starts closing this off and the water comes directly from the boiler. Variable temperature system is very simple. It uses a mixing valve. Now I show two butterfly valves here. A lot of times it's a globe valve mixing valve or a ball valve mixing valve, depending on the size of the system. But that's how this works. It's very simple. It just watches the temperature and keeps this temperature changed. So how does it control? The system should be enabled just like the others. We start the primary pumps, secondary pumps, and then once we get verification of that, we enable the boiler, and it starts the pumps or we start the pumps. So now we have a boiler flow, we have system pump flow, and the system's on. If after 5 minutes the lead pump fails, send an alarm and start the lag pump. The system hot water supply temperature should modulate the temperature mixing valve to maintain set point of 130 degrees. System hot water supply temperature shall be reset upon heating coil valve position. Reset range will be from 90 to 180. So now we can get colder water. So we can have water during those interim periods when we don't need much heating, just a little bit to trim off. We can get down to 90 degrees. So these are definitely more energy efficient. Our boiler is still up at 130 degrees, and this can be down at 90 degrees. That's the beauty of variable temperature. If the boiler hot water supply sensor shall modulate the boiler fire rate to maintain the minimum boiler temperature of around 130 degrees, or whatever the manufacturer requires, but then it will also allow it to heat up to 180. So the boiler could say, I can only go to 130, but when you need more than 130, I'll go up higher. If the system hot water supply temperature drops more than 5 degrees below set point for more than 15 minutes, alarm the system temperature. So you see that if you wanted variable flow, variable temperature, you would have this temperature profile here, and then in here you'd have that variable flow decoupler. So you'd have more than one decoupler, which is strange, but you'd have to figure that out. It's complicated, but you can have both. Monitor the hot water supply, hot water turn temperature, and outside air temperature and humidity. So how do we balance this thing? Test the pumps, boilers, and temperature mixing valve capability. Make sure they all work. Verify all coil balance control valves are 100% open. Remember, command those control valves open to the coil, and then go make sure the balance valves are 100% open. Balance the primary pump to provide required boiler leaving temperature, normally 130 degrees, but might be different. Balance the system pumps to design flow plus 5 or 10%. Measure the shutoff head and total head of the pump. Record all pump voltage, amp speed, inlet pressure, outlet pressure, and total flow. Pre-read all balance valves with the balance valves 100% open. So now we got the flow. When you set up these pumps, you're going to go to the VFD. These don't have VFDs. You're going to motor starter and start them, and you're going to check the flow with the pump curve to make sure you have, with all these valves open to the coil, you're going to make sure you have design flow. And then you're going to pre-read those balance valves without balancing, and you're going to decide what you're going to use. If you can use a series balance again or the proportional balance again, you can do that again, just the same as you did before, by pushing water to whichever one is your target valve. After setting each of the coil balance valves with the control wide open of the coil, close the control valves to bypass the coil and balance the bypasses. So then you're going to balance this bypass valve just like you did on the constant volume system, because this is a constant volume system. Calibrate the temperature mixing valve to modulate to provide the correct hot water supply temperature set point. This might be a little tricky. You're going to have the control guy there with you, and you're going to verify the temperature of this sensor. Make sure it's calibrated, and then make sure what that's doing to do is he's going to put either an offset in this temperature sensor or an offset on the control of this, because he's going to make sure that when you say, I want 130 degrees, we get 130 degrees. And if this is not calibrated properly, you won't get that. So you just need to check that it actually does. Whatever the system says it needs, we need to make sure it's actually delivering it. Verify flow and pressure drop across the boiler. Record flow in and out temperatures. Record pump flows and operating pressure. Record makeup water and water pressure, just like all the other systems. So these systems are fairly simple on their own. When you put them together, it gets a little more complicated. Okay, radiant heating systems. So radiant heating systems basically either have a pump or a valve, a small pump, that runs this zone. The zone is basically normally PEX pipe embedded in a slab. This piping is normally embedded about 2 inches down, but it needs to be closer to the top than the bottom, so it heats the top of the slab, not the bottom. And then we have an air temperature sensor, or sometimes we have a slab temperature sensor and an air temperature sensor. And we'll run this slab until we get a decent temperature. Now, radiant heating and cooling, which cooling is talked about in the cooling session. In heating, basically it's very, very efficient because the slab is a high mass and has a lot of heat, and it radiates into the room slowly over time, keeping the room warm. And actually the room temperature can be less than normally because you don't have to have air currents. It warms everything by radiation. That is very comfortable, and it can be slightly colder because, one, the floor is warm, especially if you're in your bare feet. Then the slab is warm, not cold like it normally would be. So these are really good systems. They're very, very efficient as far as energy is concerned. So how do we control it? The system shall be enabled based upon an occupancy schedule. Start the zone pump 12 hours prior to occupancy time, so the slab will be tempered prior to occupancy. During the charge period for heating, run until the slab rises or the room rises to 78-degree set point or occupancy occurs. When the occupancy occurs, we have a different sequence. For radiant heating during the occupancy, start the zone pump if the room temperature is less than 2 degrees below set point. Run until the room temperature is 2 degrees of set point. I have 78 degrees up here, but it may have been set this to 72 degrees, maybe an acceptable temperature. So whatever works. And then when we go into occupancy, it may be 75 degrees. It can be different between the two periods. Hot water supply temperature should be 120 degrees. Reset temperature set point based upon the previous charge time period. If the slab did not reach 78 degrees within the 12-hour charge cycle, increase the set point by 5 degrees. If the charge cycle reached set point within 6 hours, lower the hot water supply temperature set point by 3 degrees. Reset range should be 120 to 180 degrees. So what this sequence is doing is it's using the previous charge cycle to set the following charge cycle. So basically, if the charge cycle didn't actually work, it wasn't long enough, we didn't have enough hours, which means we don't have a hot enough water, then we'll raise the water temperature for this one. Then the next time, if this one went fine, it's okay, we'll leave it there. And on the next one, it may actually lower it, so it goes up and down. And this is a direct control loop and will work. Monitor all temperature sensors. The hot water supply temperature is below set point by more than 2 degrees for more than 50 minutes, then a trouble alarm. Okay, how do we balance this system? Test the pump operability. Verify the unit provides flow and temperature control. Balance system pump to design flow. Measure shutoff head and total flow head. Record pump voltage, amps, inlet pressure, outlet pressure, and total flow. Really simple to balance. But normally you have a lot of circuits, not just one. So let's look at radiant heat. All heating systems might have radiant heat if you're in a cold zone. And of course, these basically have a hot water pipe supply. And they have valves on them, and they go to baseboard heaters or unit heaters and back to return piping. So it's a really simple system that either two position on and off, or they might actually modulate to a room temperature. Zone can be unit heaters, cabinet heaters, radiant panels, or baseboard heaters. Anything that's heated with water. Local thermostat control or DDC control. A lot of times these are in conjunction with a VAV box or a fan coil unit. So this might be first stage heating and the fan coil may be second stage heating. Let's look at the sequence. System should be enabled based upon its occupancy, like always. Modulate the zone valves to maintain the room zone temperature set point. Monitor all temperature sensors. If any zone drops more than 2 degrees below set point for more than 15 minutes, send a trouble alarm. Test control zones operability. Verify that all control valves and balance valves are 100% open. These also should not have diversity, so all should be balanced at the same time. Balance each zone valve for the design flow. Report the zone flows. Super simple to balance. Normally they're very small, half-inch, three-quarter-inch pipes, so it's a pretty easy balance. Now we have the second time radiant zone piping, the same thing, except we have pumps instead of zones. So they can still be unit heaters, cabinet heaters, panels, baseboard heaters. Local thermostat control or DDC control. Now, I show a single baseboard heater, but there may be 10 or 15 of them in series here, depending how the designer wanted to do that. So there could be more than one in this sequence. System should be enabled based on schedule. Stop the zone pump to maintain the zone temperature set point. So basically, instead of a modulating valve, we're just starting and stopping a pump. Monitor all temperature sensors. If any drops more than 2 degrees, send out alarm. Same sequence as the last system. So how do we balance this? The same way. Test the pumps, make sure they work. Verify that all balance valves are 100% open. Balance each zone valve for design flow. I didn't mention here, but these aren't valves. We need to make sure all these pumps are actually running, and then balance each zone valve for design flow, and then report the flows. Again, very simple way to balance. And that's hot water systems, both constant volume and variable flow. Hope this was helpful. Thanks for being a subscribing member. Have a great day. Catch you on the next one. Thank you.